So in this video, I'll get you set up on the problem from exam 3 from chapter 9, and it is 9.8. We have the area shaded in blue, and we want to determine its centroid. Remember that in terms of kind of getting some intuition of where that centroid would be located, if we envision this as an actual infinitesimally thin plate of uniform density, its centroid will just be its center of gravity, or where you would actually put your hand underneath to balance. And since the majority of the area with respect to the y-axis is closer to the upper bound, which is a over 2, we'd expect that the centroid will be closer to the top of the shape than to the bottom. And since a good chunk, it's kind of hard to say where it's going to be an x. We'll just have to do in math because you do have a decent amount of area kind of spanning over to A, but that the cross-sectional area, if you take little chunks, is getting thinner versus it's larger over here. So it's the one thing you know is it's going to be closer in y to a over 2, but hard to, at least for me, physically see where it will be in x unless I had it actually printed out here. But the good news is we have all this wonderful calculus that we've learned. So we can actually just compute it ourselves rather than having to do empirical experiments to see where it's at. So the one thing that makes this problem different than the other is the irregular curve is on the bottom right. In the last example we worked, it was actually on the top. So and another way that manifests itself is any point along the irregular curve, we have the x location expressed as a function of y here. So if I take that relationship that I'm given, y cubed equals 8 squared over 8x, and I solve that for x, which you can just do by multiplying both sides by 8 over a squared, what this gives you is a relationship that if you actually put in a value of y, so if I give you a value along the vertical axis from 0 to a over 2, I can compute the value of x easily. So since I can express x as a function of y, what's going to happen here, whenever you have that type of mathematical relationship, is you want to draw your infinitesimal rectangular chunks not as vertical rectangles, but as horizontal rectangles. And here is the actual origin of your coordinate system. So if you notice this little dA, idea always kind of works the same. It's this tall and it's this wide. This is just going to be, since we're chunking up in the vertical direction, dy. And this, if dy becomes infinitesimally small, which it is just going to be a single point along that curve, which we're going to call our variable x. So we're going to allow y to vary from 0 to a over 2 when we integrate. And depending upon the value of y, so you can like label y in there if you want, you can compute the value of x. So let's actually write in our expressions. dA for any little infinitesimal rectangles that we draw in the horizontal direction is just going to be x dy. And note that we can express x as a function of y. It's just 8 over a squared y cubed dy. So that is the expression for dA. In addition, remember that we need to know the centroids of these little rectangles. They're always simply going to be, since it's infinitesimally thin, their centroid in y, which we denoted as y tilde, is just going to be wherever we're at in y as we integrate. And their centroid in x, remember that x is the height of the width of the rectangle here, so we only need to go halfway, is just going to be x over 2. But we don't want to work with x. We only want to do single variable integration. So I'll take this term in x, and I will take the term in x and express it as a function of y. Sorry, it's a late night. And actually, it's not that late. It's just this daylight savings time. So I have my x expressed as a function of y, and that whole thing is divided by 2. So if you just do some math simplification here, the 8 divided by 2 will give you 4. This is going to be 4 over a squared y cubed. So this is the centroid of the infinitesimal rectangles in x as a function of y, and this is the centroid in y. So I'll show you how to actually set up the computation for the centroid of the entire shape in x, and then you can repeat it for y. So your formula that you need to use is that x bar times integral dA equals integral x tilde dA. And if you think about these again, if you think about the a's as weight, what this basically says is that, remember, you're going to put like the centroid somewhere here, so that x distance is measuring the distance from the y-axis. So if you were to view this as a homogeneous plate, this is basically the moment of the equivalent concentrated force about the y-axis is equal to the sum of all the individual little moments associated with these rectangles. But you don't actually have to think about that. You just know you're trying to determine what x bar is. So you can just write it as integral x tilde dA divided by integral dA. And it's just a matter of now plugging everything in that we have above hand. So let's actually plug in for dA, this expression that we have here, 8 over a squared y cubed dy, and we're going to allow y to vary from a range of 0 to a over 2. So this is going to be from 0 to a over 2 in y. And then in the numerator, right, again, we're varying y from y equals 0 to y equals a over 2. What expression do we have for the centroid of the little rectangle in x? Well, remember that is over here. It's just going to be 4 over a squared y cubed. And then dA is just going to be everything that we had down here, 8 over a squared y cubed dy. So even though it looks like it's relatively complicated, it's actually not. So let's, in the numerator, pull out the constants. Remember that anything that doesn't involve y is a constant, including this a is just a geometric parameter of the shape. So in the numerator, you have 4 times 8, which is going to be 32 as your constant. And in the denominator, you're going to have a squared times a squared, which is going to be a to the 4th. I should say that's in the denominator of that term that you're pulling out of the numerator. So this is integral from y equals 0 to y equals a over 2. And then what do we have left after we pulled out the constants? Just y to the 6th dy. What about in the denominator? We have an 8 over a squared term. And then inside, integrating from y equals 0 to y equals a over 2, you have the term y cubed dy. So let's actually do these integrals. 32 over a to the 4th. This is just, in order to compute the definite integral, we need to take the antiderivative of what's inside. The antiderivative of y to the 6th is y to the 7th divided by 7th, divided by 7, I should say. So y to the 7th divided by 7. And we're going to evaluate that from y equals a over 2 to y equals 0. And then in the denominator, we're only integrating y to the 3rd. So that's going to be, I still have my constant, 8 over a squared. The antiderivative of y cubed is y to the 4th divided by 4. And I'm going to evaluate that from y equals a over 2 to y equals 0. So I'm going to clean up the numerators a little bit. I'm going to pull that 7 out. It's going to be 32 over 7, a to the 4th integral. Or I should say y to the 7th evaluated at a over 2. So that's just going to be a to the 7th divided by 2 to the 7th minus y to the 7th divided by 7 evaluated at 0. That's just going to be 0. In the denominator, I have 8 over 4a squared. And should have probably cleaned that up and canceled, but we'll do it a little bit later. And then inside, when I evaluate y to the 4th at a over 2, that's just going to be a to the 4th over 2 to the 4th. And then when I evaluate it at 0, that'll just be 0. So let's clean all this up a little bit. We got 32, we got an a to the 7th, and in the denominator, we got a 7 times 2 to the 7th times a to the 4th. I don't really want to do that math because I have a feeling there's going to be some cancellations here. I'm kind of doing this problem on the fly for fair warning. And then in the denominator, we have 8a to the 4th divided by 4 times 2 to the 4th a squared. So I'm going to clean a little bit up here. I'm going to say that I'm going to cancel these 4 factors of a with 7 of the 4. So that'll be 32 a to the 3rd divided by 7 times 2 to the 7th. And down here, I'll cancel the 4 into the 8. So that's going to be 2a to the 4th over 2 to the 4th a squared. And I'll cancel the a squared into the a to the 4th. So this would just be 2a squared divided by 2 to the 4th. And then remember that when you divide fractions, you multiply by the inverses. This is where I'm hoping I'm going to get lucky with my weird many factors of 2. So here I have 2 to the 7th. And then when I divide by this, I'll multiply by the inverse. So it'll be 2 to the 4th over 2a squared. Okay. So I'm going to cancel a squared into the a to the cube. That'll leave me with just a. Now let me be careful here. I'll take these 4 factors of 2 and cancel into the 7. That's going to leave me with 2 to the 3rd. And let's clean up the actual arithmetic here a bit. It's going to be 32a in the numerator divided by 7 basically times 2 to the 3rd times 2 is 2 to the 4th. And as we anticipated, and believe it or not, I still remember working problems like this from when I took the class a long time ago. They're just annoying. 2 to the fourth is 2, 4, 8, 16. So you can write that as 32a over 7 times 16, and then cancel the 16. And you basically get 2 sevenths a. That is the centroid in the x dimension. So let's actually look at where that would be at. Remember, this is a wide, so 2 sevenths of the way over is where it's at in x. So all that you need to do for the actual exam problem now is to complete this for y bar. And the way you're going to complete it for y bar is y bar is going to be integral of y tilde dA divided by integral dA. But you already have this. That's an integral that we've already computed, and you have it relatively simplified. You could take a different approach, and the only thing that you need to do is substitute in y bar. Remember, y bar is actually equal to y. Here is dA as a function of y, so your integral will be a little bit simpler, but basically the same thing. So hopefully that gave you some decent idea of how to get that problem started on the exam, and hopefully all of you will at least get half of that question right without having to do any work. So I will actually pick up and see you again on these. I'm going to do a similar thing for Chapter 9. I think if I recall, there's 2 questions from Chapter 9, so that this lecture might be a little bit longer, but I will see you all soon.